renewable energy sector is growing rapidly as an increasing number of countries are switching to alternative and carbon-neutral sources of power. To prepare us as future engineers, we were tasked with designing and building a micro wind turbine to be tested in a wind tunnel. From an aerodynamics perspective, our objective was to achieve a maximum power coefficient at a chosen design TSR. After conducting research from various sources, such as research papers on wind turbines, we were able to better define the project scope and direction. Our key findings included the following. Our turbine should be two-bladed, as such a turbine has a higher performance-to-weight efficiency at lower wind speed as compared to the more commonly seen three-bladed wind turbine. We also found that we should aim for a TSR of approximately 2 pi, since this is where the power coefficient is found to be the highest, based on empirical data. We decided to optimize the airfoil for the maximum speed of 12 meters per second. We looked at possible airfoils to be used, and based on our findings, as well as successful turbines from previous years, the SG6043 airfoil was seen to be a strong candidate due to its high lift-to-drag ratio and enough thickness. Our restriction was a maximum rotating speed of 3000 rpm, and this corresponds to a maximum tip speed of 124.1 meters per second. As a general guideline, a larger swept area corresponds to a larger power output. We decided to avoid any abrupt changes in the shape of the turbine at the root and at the tip in order to minimize drag. Finally, we ensured that our design would feature a slender tip rather than an abrupt tip in order to reduce losses. With these findings in mind, we went on to calculate the parameters of the turbine. Firstly, we calculated the optimum chord lengths using Schmidt's theory along the blade section. The optimum chord length should be inversely proportional to the radius. The theoretical induction factors, along with phi, which is the angle between the plane of rotation and the relative velocity, were calculated. Whilst the angular velocity of the blade is constant, the linear velocity increases as r increases. This means that the direction of the oncoming wind seen by the blade changes, meaning that the local angle of attack also changes. Subsequently, values of relative velocities at each section were obtained and used to calculate the Reynolds number at each discretized section of the blade. Using these Reynolds numbers, we found the optimum angle of attack corresponding to CL max for the chosen aerofoil for each section in Q-blade. We then decided to test the design on Q-blade to ensure that the turbine was spinning in the correct direction and that there were no aerodynamic anomalies. Specifically, we looked to see if our wind turbine would stall.
To ensure that the blade is able to operate under the required test conditions without structure failure, the centrifugal and aerodynamic forces subjected on the blade at 12 meters per second were evaluated. Due to the nature of the project, other sources of load such as the gravitational and fatigue loading were neglected. The centrifugal forces were calculated using the following equation, while the aerodynamic forces were obtained using the blade element momentum method, in which an iterative process is employed to calculate the induction factor at each section of the blade. By interpolating the coefficient of lift and drag curves imported from Q-blade for the SG6043, the CL and CG values at a particular angle of attack required for each iterative process were obtained. Additionally, Prandtl strip loss was accounted for in a DEM method. The blade was idealized as a cantilever beam, which allowed us to take moments at each section of the blade and evaluate the resultant stresses. The moment of inertia of each section of the blade required for the stress calculation were found using Autodesk Inventor. By obtaining the stresses due to the centrifugal and aerodynamic forces, it was found that the maximum stress experienced by the blade would not exceed that allowed by the material, even after a 20% reduction factor has been applied to the material stress limit to account for the direction of 3D printing. The stress calculations were subsequently cross-checked with those obtained through the FEA simulation on Inventor, whereby the aerodynamic forces at each section of the blade were evaluated as a vertical point force with the quarter chord length along the span of the blade. The stress analysis showed that for the SG6043, our blade will experience a maximum deflection of 11.3 centimeters. This proved to be quite concerning, as although the blade would not break, this could significantly affect its aerodynamic performance. As such, a decision was made to switch our aerofoil section to the SG6042, which offered a thicker section. By performing all the calculations, FEA showed a 60% reduction in maximum deflection, from 11.3 cm to 4.4 cm. Since our minimum viable product requires a mass lower than 200 grams, the blade was hollowed from the root up to 54% of the blade length, with a shell thickness of 1.8 mm. This reduced the total mass by over 28%, while only increasing the deflection by 6.42%.
Since we chose to use a thicker airfoil to satisfy structural demands, we drew our inspiration from birds such as the barn swallow and the owl because of their thicker airfoil wings. These birds have a slightly curved leading edge and minimal sweep. Adding sweep to our turbine increases its ability to catch the wind at low wind speeds and increases power coefficient. Hence, the next stage in our design process was deciding on the best sweep characteristics. After consulting various research papers, we found that a backward sweep starting at 80% to 90% of the total blade length and restricted to 5% of the blade length at the tip avoids an excessive increase in blade root torsional moments.
The shape of the hub was an LV hat that is defined by this equation. The LV shape is given when C is equal to 1/3 and is the optimum drag for a given volume and length, allowing us to keep the hub as small and as lightweight as possible. Since we wanted to make the hub as large as possible, the turbine needs to be foldable during the printing process to satisfy the requirement of being printed as a single part. As such, a hinge mechanism was designed. The placement of the hinge needed to be on the hub, as hinges on the blade would disrupt the airflow. Originally, the hinge was going to be a butt-style hinge, like that seen on most doors. However, we felt that since this type of hinge only has rotational freedom of movement, we would not have enough tolerance in the printing process to ensure a good join between the two halves. Therefore, a sliding block mechanism was designed, giving us the right amount of freedom of movement in all three axes.
Our first step in manufacturing the turbine was to create the hub. This was done via a combination of CNC turning, lasing, engraving, as well as 4-axis machining. After completing the Creo drawings in CAD files, the blades of the turbine were 3D printed using ABS plastic and a sewable support material. The challenge of 3D printing a hollow section was overcome by leaving several holes in the section surface of blade, allowing for the support material to be removed in an ultrasonic bath at a later stage. Once the blade was removed from the bath, we glued the hub into the blade using an epoxy glue. We then sanded the blades in order to ensure a smooth surface, which will result in less skin friction drag. The turbine was tested in the 1.11 by 1.66 meters wind tunnel at 6, 8, 10 and 12 meters per second and was able to operate safely at all 4 test conditions without stalling and displaying noticeable deflections. However, we did observe resonance of the blade at 2 frequencies. We obtained a range of power coefficient between 0.15 and 0.216. The TSR at max power coefficient varied between 5.1 to 5.9. The highest power achieved was approximately 65 watts at 12 meters per second.
We estimated our maximum CP would occur at a TSR of 2 pi. However, results show that our maximum CP occurred at a TSR of 5.871 instead. This is roughly 6.6% slower than our estimate, which means our blade was optimized for a lower rotational speed than it was designed for. Our maximum CP was only 36.6% of the BETS limit, which suggests that blockage did not have a significant role in impacting our results. Despite this, a certain level of blockage was still present, as the swept area of the blade was still 15% of the tunnel cross-sectional area. Resonance was also present during our wind turbine testing, which is evident in the noise found in our CP distribution. Upon reflection of our design process, we noted that we did not conduct sufficient analysis of the aerodynamics of the root. This is because we created a large surface at the root, causing an increased amount of drag while producing the same lift, leading to a loss of power. This could explain our low CP value. The lack of root analysis also affected the max power TSR value, since we did not consider our root during the optimization. The large chord and twist of the root section meant that the blade would be optimal at a lower TSR than was estimated. The FEA analysis also overestimated the maximum deflection of the blade, as the deflection observed during the test was significantly lower than the predicted 4.47 cm deflection. This can be attributed to certain inherent assumptions made within the analysis model in Inventor. In retrospect, the SG6043 would have been a more suitable choice for better aerodynamic performance. Nonetheless, FEA in Inventor was able to provide a stress approximation which cooperated well within our calculations. Our swept wingtips were very thin and therefore fragile. This made sanding them to a smooth finish difficult. Surface roughness could have nullified any advantage contributed by the wingtip shape. Additionally, a pause during the manufacturing process led to lines printed along the length of both blades on the upper and lower surface of the blade, near its leading edge. This could have caused the boundary layer of the suction surface to chip, significantly lowering the performance of the blade.
In summary, whilst our wind turbine did not perform as well as we expected, it did satisfy the core objectives of the brief. From a structural perspective, the wind turbine was well engineered, but we could have improved the design by including a greater focus on the aerodynamics of the roof.